let me outline how my talk will take part. First, I will explain the main ideas in a qualitative, non-technical level, and then I will get technical. First, I will explain essential and inessential aspects of Bohmian interpretation, and then I will explain how reduced non-locality can be obtained from reduced particle ontology in the Bohmian framework. Then I will discuss the case of many observers, and finally the conclusion. So first, the main ideas. As we all know, the Bell theorem leads to two confronting views. One is non-realism, according to which nature is local, but objective reality does not exist. And the other is realism, according to which objective reality exists, but is not local. And as we know, there is a lot of fight between these two groups. There is a typical dialogue between them, looks like this. The realist says, how can you believe that things do not exist before measurement? It doesn't make sense to me. And non-realist replies, how can you believe in hidden variables which cannot be observed? It doesn't make sense to me. And in a sense, they're both right to a certain extent. So motivation is to reduce the confrontation between these two views, or to demonstrate that there is an intermediate option which is at least not impossible. Even if not very convincing, it is possible in principle. So for that purpose, I proposed a hybrid approach, which means some elements of each of the two views are combined into a new interpretation. And this new interpretation, to a certain extent, we shall see which extent, it remains both objective reality, retains both objective reality and locality. But there will be a price to pay for such a strange combination, and that will be solipsistic reality. This is a term from philosophy, which means the view that subjective mental experiences are the only true reality. So we shall see how a version of Bohmian mechanics leads to such a solipsistic reality. So let us start with some old philosophical questions. Well, one possibility that what we observe is not real. Or perhaps there is a possibility that whole universe is only in our minds. That are typical philosophical views on that context. But let us get back to quantum mechanics. The orthodox view of quantum mechanics, or at least one version of it, is there is no reality except the observations. And according to this, all observations are local because they happen somewhere in a local place, for example, in the brain. So in that sense, the local. But the question is, can these local observations correspond to something real, which is still local? And the answer is yes. For example, some objective processes in the brain. They're local in the sense that, if we have separated particles at a very large distance, the coincidence, the observation of coincidences still happens for example, in the detectors of coincidence counter or in the brain. So that's how it can be real and local. But the problem we have is when we have two observers, let us call them Alice and Bob. Well, if we have locality, that means that Alice's observation are not correlated with Bob's observation. But from quantum mechanics, we know that Alice can hear that Bob says what his observation is, and it must be correlated with other Alice observations. But it is important to stress that this correlation is correlation between one Alice observation with another Alice observation. So Alice cannot read Bob's mind, so theory does not need necessarily to predict correlations between Alice observations and Bob observations to be consistent with observations we have. So that strange interpretation, I will show that such a local solipsistic reality actually naturally emerges from a simple variation of non-local Bohmian interpretation. But first, let us explain the Bohmian interpretation. The standard approach is a top-down approach. First postulate that there are particle trajectories, and then explain why such trajectories are compatible with quantum mechanics. But to understand more deeply why Bohmian mechanics works, I will present a reversed bottom-up approach. I will first present interpretation-independent essentials of quantum theory of measurements, and I will explain what are its problems. And then I will ask what kind of new objects should we have to solve these problems, and that will lead in a few steps to Bohmian mechanics. So first, interpretation-independent theory of quantum measurement. Suppose we have some observable k with eigenstates k, and we have measuring apparatus with some initial state phi 0. And if we have interaction, then we have a unitary transition of this form. And these phi states can be macroscopically distinguished. That's important property. So that means that the wave functions have a negligible overlap in configuration space. And in configuration space of the apparatus, we have n particles. So this small n is number of particles that constitute the apparatus. And the important property is that they do not overlap, or overlap is negligible. And if the initial state is a superposition, then after the interaction, we have a superposition of this form, including the states of the apparatus. And effectively, for phenomenology, we know that the state collapses to only one of these states. So we want to explain it. And it is again important that phi can be macroscopically distinguished. So this superposition consists of many branches that can be distinguished. So each branch evolves as if other branches did not exist. That's important property. So from perspective of any particular branch, other branches do not exist. And that explains the collapse, provided that one remaining question can be answered. Why should we take a view from the perspective of one branch as the physical one? And unfortunately, there is no interpretation-independent answer to this question. So we need some interpretation. So possible answer to the last question is because wave function itself is the only physical object. And that leads to the many-world interpretation. But there is a problem, because Born rule in the many-world interpretation cannot be explained without additional ad hoc assumptions. So let us try with a different answer. Particular branch becomes physical because it becomes filled with something which is physical. So in that case, entity which fills one branch should not fill any other branch. And that means that filling entity should be well localized in configuration space, because branches are well localized in configuration space. And that means that filling entity must be described by a position in the configuration space, where n is the number of the particles constituting the apparatus, because the apparatus has non-overlapping wave functions. So that means that apparatus is made of point-like particles. These point-like particles are the things that enter one particular branch. However, apparatus particles do not necessarily be the only real physical entity. So if apparatus particles are real and point-like, it is natural to assume that all particles in the universe have this property. And in this case, to remind, small n is the number of particles in the apparatus, and big N, capital N, is the total number of particles in the universe. So they can all be real. And we have the probability density of all particle positions in the universe given by psi squared. But this probability density cannot be tested in practice for the simple reason one cannot observe all particles in the universe. In reality, so one really observes macroscopic observable describing the measuring apparatus. This is what we really observe. So phenomenologically more interesting is the apparatus probability density, and how to obtain this. It is just by tracing out all the other degrees of freedom of the total probability density. So the apparatus density, due to non-overlapping feature of these wave functions, takes this form. And then the probability to find the apparatus particles in the support of wave function phi is given by this expression here. This is just a standard probability calculus, and this is actually the Born rule. The final result is the Born rule. So we see that it is sufficient that only apparatus particles exist, because that's how Bohmian interpretation explains the outcomes and the Born rule. And only them really need to have the quantum probability distribution. But how to achieve this? Well, a simple way to provide this is to require that all particles exist and have the quantum probability distribution, because in this case, this is just, how we trace out the unknown other positions of the particles. But I didn't yet speak of particle trajectories, which are typical for Bohmian mechanics. So why do I need them? Well, probability density in general depends on time, so particle positions should depend on time, and that leads to particle trajectories. Trajectories may be smooth, which means that velocity should be well defined. So what law of the velocity should we obey? We search for the velocity law. Well, we need the compatibility with quantum probability density for all particles, and that means that velocity function must obey the continuity equation. And there is a simple choice for this continuity equation, is that these velocities here are given by the Bohm velocities. In that case, the continuity equation is obeyed. The Bohmian velocities are given by this formula here, where VA is the velocity operator given in terms of momentum operator. So the velocity of particle A is given by the well-known expression. And it is non-local. Why? Because it depends on positions of all particles in the universe. Big N means all particles in the universe. And this is a consequence of the fact that we assumed that all particles have positions. But on the other hand, we have seen that only apparatus particles are really essential to explain the Born rule, which you observe. So if only those particles of apparatus exist, perhaps it could avoid non-locality, and in the rest, I will explore that possibility. So we start from the same continuity equation for all particles in the universe, but we integrate out all the positions except the apparatus. So all the other positions are integrated out in the initial equation for the continuity. So what we get the small n. Okay, only apparatus particles remain as variables, because all the others are integrated here and here. But here the summation is split into two parts. Here the summation is only over the apparatus particles, and here the summation is over all other particles. And due to Gauss' theorem, the last term is a surface integral which vanishes, so only the first line remains. And we get a new apparatus continuity equation. This is very similar to the initial continuity equation, but here we only have positions of apparatus particles. And we have a new velocity in the continuity equation, which is related to the Bohmian velocity, but not exactly the same, because again, the other positions are integrated out. This integral over all other positions can be written more elegantly in terms of particle or partial traces. We introduce a standard density matrix. Then apparatus density are diagonal matrix elements of the reduced density matrix. Here the traces over all no apparatus particles. And the velocity can be written elegantly in terms of traces. Okay? So measurable predictions of quantum mechanics can be reproduced by postulating that particles have these trajectories with these new velocities. But it has important properties. First, only the apparatus particles have trajectories. You see only small n here. And the velocity of particle B of the apparatus depends only on the other positions of apparatus particles, not on positions of any other particles in the universe. So that makes the theory much more local than standard Bohmian mechanics, and still it produces predictions of quantum mechanics. Now consider example. Consider EPR source with two particles and two detectors and one apparatus. Here, the important thing that apparatus is there is only one apparatus, which is a local object. So before the detection, we have this wave function of the EPR source, and after detection, we have a total entangled wave function for all the detectors and the apparatus. And the question is, how are new hidden variables, which are particle trajectories, avoid the non-locality of the Bell theorem, because we have EPR setup? Well, the Bell theorem assumes that hidden variables associated with entangled particles of the source, and also with separated detectors. If such hidden variables exist, then Bell theorem says that such hidden variables must be non-local. But in our case, such hidden variables do not exist, because hidden variables are attributed only to local measuring apparatus. As you have seen here, only here we have hidden variables. Okay, now let's again be a little bit philosophical. Well, the question is, what kind of measuring apparatus could be more real than anything else? Because we are saying that only apparatus is real, so what does it really mean? What kind of apparatus is that? Well, perhaps it could be brain. Or perhaps could be only neurons responsible for consciousness. Or perhaps something more directly related to consciousness. We don't know what it is, but whatever it is, we call it observer. But then there is the question of, when you have many observers, let us have two of them, Alice and Bob. Before observation, we have entangled particles, and after that observation, we have the entanglement with Alice and Bob states, and position and Alice and Bob particles are different positions of Alice particles and Bob particles. And then we have independent Alice and Bob velocities and independent Alice and Bob probability densities, and which satisfy independent Alice and Bob continuity equations. So Alice and Bob are really independent, which is a consequence of locality, this theory. So look, due to locality, that means that Bob particle velocities do not depend on Alice particle positions, and vice versa. And Alice particles may not feel the same branch of the wave function as Bob particles. This is different from non-local Bohmian mechanics, where all particles fill the same branch. But the question is that consistent? What if Alice and Bob measure the same observable? That's probably the most interesting question. So let us consider a simple state, both measured by Alice and Bob. Well, it is possible that Alice is in branch up, while Bob particles are in branch down. So in that case, they disagree whether the spin is up or down. And this seems to contradict the predictions of quantum mechanics, but actually it does not, because neither Alice nor Bob can observe any contradiction. Why? Because Bob particle positions are hidden variables for Alice, and also Alice particle positions are hidden variables for Bob. So this is just the solipsistic interpretation, in other words, because Bob's mental experiences are hidden to Alice, just as Alice's mental experiences are hidden to Bob. And now the conclusion. So the Bell theorem against local hidden variables does not exclude local solipsistic hidden variables. Solipsistic hidden variables associates reality with observers, but not with observed objects. A model for solipsistic hidden variables is provided by a variation of Bohmian interpretation. In that interpretation, different observers are not correlated, but all observable predictions are compatible with those of quantum mechanics. Thank you.